Hey there, my name is Alejandro, and welcome back for day 91 of me doing the Daily LeetCode Challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for October 15th, 2024. Let's get straight into it. Okay, today we got LeetCode medium problem 2938, separate black and white balls. Okay, there are n balls on the table. Each ball has a color black or white. You are given a zero-indexed binary string S of length n. Okay. Wait, there are n balls? Okay, you're given a zero, okay. Indexed binary string of length n, where 1 and 0 represent black and white balls respectively. In each step, you can choose two adjacent balls and swap them. Return the minimum number of steps to group all the black balls to the right and all the white balls to the left. Okay. So if you want all the white balls to the left, then however many white balls there are, okay, if there are, so yeah, for example here, so 0 means white or 0 means black. Let's see. Because you want all the white balls to the left. Black and white. So white is 0. Okay, cool. 1, 0, 1. So here would be 1 because you need to put the 0 to 1. Don't you just want, okay. So essentially, okay, we can do this as step 1, count number of white balls. Step 2, call this number num white balls. Step 2, return num white balls minus number of white balls in first num white balls slot. Well, actually, even better, count number of black balls in first num white balls slots. Okay, so essentially here, s.count the number of black balls. We're going to say, okay, black comma white is equal to 1 and 0, right? Okay, so now s.count the number of black balls, of white balls. We're going to call this num white balls, num white balls. Okay, and now essentially, okay, so this is the number of white balls there are, right? We want all the white balls to the left. So however many in the first left num white balls numbers there are that are not white is how many we need to swap. And all the ones that are not white are essentially going to be the number of blacks, right? So here we return s.count return. Ooh, I could even do something like this. Because, okay, if I do sum with this, does it automatically convert them to integers? Okay. Return sum of ball equals black, or ball doesn't equal white for s of ball in range, or s of ball for ball in range, s of ball index for ball index in range up to num white balls. Does something like this work? It does not. So why does it not work here, right? So here we have two white balls. Oh, it only takes one swap to bring it in there, right? Okay. So we don't have to swap them, right? Wait. Why wouldn't this work here, right? So here num white balls is 2. So for I in range 2, 0 and 1, the sum. Oh, so here it's saying I need 2 swaps. Oh, you can choose 2 adjacent balls and swap them. Ah, okay. I read the problem incorrectly. Okay, so we should definitely have, okay, so we can scrap this idea. Step 1, okay. Let's think about this more carefully. Okay, so step 1 is correct. We should do this, right? Count the number of white balls, right? And then num black balls is equal to length of S minus num white balls, right? So however many white balls there are, the rest must be black balls, right? So we can definitely use this at the very beginning. So that's cool. Return the minimum number of steps to group all the black balls to the right and all the white balls to the left, right? Essentially, it's just like, you're just gonna keep going until it's valid, right? You're just gonna keep making swaps, right? So here we're gonna say num swaps is equal to 0. I is equal to 0. While I is less than length of S, while I is less than num. Okay, I gotta think, right? Okay, so this is not that trivial. Okay, I gotta think. So I'm gonna swap things together, right? So let's just pause back. Let's think. Let's not rush things. So the point is, like, if I have 1, 1, 1, 1, 1s, and a 0 up here, the number of swaps it's gonna take for this 0 to get to the beginning, it's gonna be a lot, right? So, okay, I can also do this greedily, right? Where it's like, okay. Whatever first white ball I have, I'm gonna put that at the leftmost index. Whatever second ball, okay. This is gonna make a lot of sense, right? Okay. The first white ball, I might as well put it in the very first index, right? So however many swaps that's gonna take. Then, the second, and I can just, okay, and I won't interfere with another white ball because it's the very first ball that I see. Okay, and then the second white ball that I see, okay, the second ball that I see, I'm going to want it to be at the second index, right? And so it's whatever index it is, however far it is from the second index, that's how many swaps I'm going to have to make, right? Okay, this is actually going to be, okay, so it's still a simple problem, it's just different from what I initially thought, right? So here, it's going to be num seen is going to be equal to 0, and our index to place, we're initially going to put index 0, right? So the idea is that we're going to put leftmost white ball to leftmost index. Then second leftmost white ball to second leftmost index, i.e. index equals 1. i.e. index equals 0. Keep on going until this has been done for all num white balls. Okay, num white balls seen. Num seen. Number of white balls seen so far. Leftmost index, or index. Index to place next white ball to, right? Okay. So here, we're gonna say, okay, well, num seen is less than number of white balls, right? And here we're going to do I equals 0. And here we're going to do loop invariant I plus or equal to 1. We'll just put that assert in there because it should always be true, and then at the end we'll remove it. Okay, let's drink some water. We got this. This is not too bad. I just had to think of it for a little minute there, and now we're Gucci. So now I'm just gonna carry on with this idea. While num seen is less than the number of white balls, then yeah, okay. If we'll do ball is equal to S of I. Ball index, right? And we'll just, there we go. If ball is equal to black, continue, right? Otherwise, ball is white. Need to place it at leftmost index available and count number of swaps that would have taken. Right, so okay, let's think about it. If we've seen one at index 2 and we want to place it to index 0, then from index 2 we need to swap it with index 1, and from index 1 we need to swap it with index 0, right? And so let's think, okay, if I wanted to go from 4 to 1, I have to go from 4 to 3, 4 to 2, 4 to 3, 3 to 2, 2 to 1. So 4 minus 1, yeah, three steps. So I just wanted to make sure I'm not plus or minusing 1 here, but essentially we want our current index, which is ball index, minus, I will call this leftmost index. So we're gonna add this to our num swaps, right? Plus or equal. Then we're gonna do leftmost index plus or equal to 1, because that's where we want the next white ball to be, because again, we want all the white balls to the left. Right? And what else? Number of seen. Num seen plus or equal to 1. Number of swaps needed to get white ball. Okay. Number of swaps needed to get white ball to index leftmost index. Want next white ball to be at index adjacent to leftmost index. Take into account the fact that we've just computed increment number of white balls seen / taken care of so far. And we'll put this all together because they essentially belong all together, right? It does look cleaner when I have it like this, right? Maybe I put two spaces there just to kind of separate the two. Okay, so if the ball is black, then we can. Okay, you know what? We'll do this better. There we go. If ball is equal to white, then we're gonna do all this stuff, right? Because we want the loop invariant for both steps anyways. There we go. And that way the comments are a bit more nice, right? And there we go. So it makes it just a tad more sensical. And then we always have our loop invariant here, right? So there we go. If ball is white, we essentially take account for the number of swaps it takes to put it to the leftmost index. We know all of those are black, right? Because this is the very first one that we've seen that is white. And then we put it at leftmost index. So we now update our next leftmost index to be the second leftmost index, and then third, and so on. And then again, when we know that we see another white ball, it'll take that many swaps to get it back, right? And there's never going to be a case where it's like, even if I swap two white balls together, no, the point is that that can't happen, right? Because I get the first white ball, put it to the front. Second white ball, put it to the front, right? Is there ever a case where I have, a bunch of ones, I have a 0. Even if I have my 0 here, right? it doesn't matter if I swap these two zeros together. Like, actually it does matter because that gives me an extra swap. I still have to swap these guys, swap these guys, swap these guys, swap these guys, and swap these guys. And then come back to here and swap these guys, swap these guys, swap these guys, swap these guys, and swap these guys. So I can't get around that anyways, right? So I think this is okay. I just gotta think here. I mean, we might as well try running it, but let me think if I'm missing anything. Num swaps. Oh yeah, so here we're gonna keep track of num swaps is equal to 0, result to return, right? And here we're gonna do return num swaps. Okay, it passes, submit. Okay, there we go. We seem a little slow. Okay, it just might be, okay. It just might be our constant stuff, right? So we definitely don't need this, for example. We don't need this, we could just do, it's fine, right? Yeah. I mean, okay, so you have to count the number of white balls, right? So you can't do this in less than O of n time, right? Because you need to at least know how many there are for swapping. Can get rid of this. And then, yeah, if I iterate through all the balls again, doesn't matter, right? Because I always have this assert over here. So I might as well remove the assert for now. And there we go. Okay, so let's just submit one more time. And there we go. Okay. We're not too far from other people's submissions over here and so on. We're just a little bit on the right of the peak. It might just be your like constant time stuff and so on, but okay. Very, very nice. Okay. Okay, so this was a nice little solution. Just a nice little greedy one. Okay, so as always in all my videos, I do a quick recap of how I was able to solve the problem. And this one essentially is just that we essentially have a 0 index binary string S of length n, where 1 represents a black ball and 0 represents a white ball, right? And the idea is that we want to return the minimum number of steps to group all the black balls to the right and all the white balls to the left. So if we group all the white balls to the left, naturally all the black balls will be to the right? Like if you have all the white balls to the left, the only other possible thing that can be on the right is all the black balls, right? And the black balls, you know, they're not unique or differentiable in any single way, so it doesn't matter how they're sorted, they're all black, and therefore you're done with the problem, right? So essentially we can convert this problem into just figuring out, okay, how do we get all the white balls to the left and what's the minimum number of moves that we can do so, right? And so the way that we can do this is, first of all, like, okay, let's count the number of white balls. Ooh, maybe that's how people, okay, maybe this is how people did it faster, right? Maybe I comment this out, and then here I just do while ball index, while ball index is less than length of S. I bet you this still works. Yeah, okay, and now I submit. So now I just do 1 O of n scan instead of 2 O of n scans. Okay, and it's telling me I'm slow, but obviously like there's no way, right? If num seen is equal to num white balls, then break. And there we go. Maybe now I'm faster. Okay. Yeah, okay. Technically, it takes O of n time to see how many number of white balls is, so I might as well not include that, right? So here, this is actually useless, and this is useless. No, this is useless. And this will still work. And there we go. Okay, so now we submit. Okay, it still seems a little slow, but okay, no worries. But okay, moving on. Essentially how I was able to solve this problem is, again, we just take care of how to move all the white balls to the left side, right? And so essentially the way that we do this is like, okay, we know we want all the balls to the left. So we might as well say like, hey, we can only swap elements together, right? So it doesn't matter if you have like zeros followed by each other and so on. What happens is that if you have like, let's say a bunch of ones followed by like, you know, 2 zeros and so on, maybe you have another 0 and so on, you have to like alternate this 0 like over here like this, and then this one like this, and so on and so on and so on. You cannot take advantage of the fact that, you know, like 2 zeros are next to one another and so on to like kind of like ship them both at the same time or whatever. You can't really do that, right? So you might as well take whatever is the leftmost 0, right? And bring that to the leftmost index, because all the zeros have to be to the left, right? So why not take whichever one is the leftmost 0 and bring that over to the leftmost index, right? Because why take this guy and put it to the leftmost index, and then, you know, like let's say this guy and put it to the thirdmost index, right? Why do that? Why not just put this 0 to the leftmost index, right? It'll probably be the same, right? But you'd have to know however many number of white balls are at the beginning and so on, which we could do like we did here at the beginning, but essentially that's not too useful. So my idea essentially was like, okay, whatever is the leftmost 0 in the entire string, we're gonna put that at index number 0, right? And then the second leftmost 0, we're gonna put that at index number 1, right? And then the third 0, we're gonna put that at index 2. And then the fourth 0, we're gonna put that at index 3, right? So it's like, you want all the white balls to the left, so you might as well put the one that's leftmost in the string at index 0, then the second leftmost at index 1, and so on and so on and so on, because you might as well do it that way, right? And so essentially the way I did this is like, okay, we're gonna loop through the string and we're gonna keep searching for a white ball, right? So here we haven't seen a white ball, and remember, we want the very first white ball that we see to be put at the very first index, right? So we're gonna say our leftmost index that we want our next white ball to go is at index equal to 0, right? And the only other thing that we keep track of is the number of swaps, right? Because that's essentially what we want to return, right? The minimum number of swaps. So initially it is 0 until we have done the whole string, right? So essentially what we're going to do is we're going to keep parsing the string until we have found a white ball, right? And we're going to keep track of our current index, right? Our ball index. So here it's like, okay, is this a 0? No, it is not. So we're going to increment our ball index by 1. Is this a 0? I.e. it's a white ball, right? It's not. So we're going to increment our current index by 1. Is this it? No, so we increment by 1. Is this it? Nope, so we increment by 1, right? And then it's like, here, augment by 1, augment by 1, augment by 1, augment by 1, right? So we're going to add 4 more here, right? So let's just do 8. And then the next one here that I come to, it's like, uh-oh, it is a white ball, right? So here's the important part. We want all the white balls to the very left, right? Since this is the leftmost white ball, again, we need at least one of the white balls to be at the leftmost index of 0, right? So we might as well pick this ball to go to the leftmost index, right? And so how many swaps is it gonna take for this guy to go to the leftmost index? Well, the leftmost index currently is equal to 0, right? So it needs to go to the very first index. And so it needs to keep swapping, right? Which means it needs to swap with this one, and then with this one, then with this one, then with this one, then with this one, this one, and this one, and this one, right? And so until we get to this leftmost index. So we're at this current index, we want to get to this one, right? So essentially what it's gonna be here, actually this is this is index 8. It's going to be this value minus this value, right? That's the number of swaps it's going to take. Here, if we do 8 minus 0, it'll be that we swap this 0 and this 1. So that's 1 swap, 2 swaps, 3 swaps, 4 swaps, 5 swaps, 6 swaps, 7 swaps, and 8 swaps, right? And now we have made this 0 come here. So essentially you can see it's this ball index minus this leftmost index, right? Because we were at ball index, we want to reach leftmost index, and we can only swap by 1 at a time. So it's going to take ball index minus leftmost index number of swaps to get there, right? So it's like if leftmost index is like 2, right? We don't need to get to all the way up to 0. We can skip the last 2, which is why we subtract by leftmost index. And obviously we're at ball index, so it's however far apart those two indices are from each other, because again, we can only move 1 at a time, right? And then from this point on, okay, so we move in here. This is now a 1, right? And now we move on to our next index, right? So index 9. And now our leftmost index is 1, right? Because we want the next white ball to come at this index, right? We already have a white ball at index 0 now, right? So the next white ball is going to be the second leftmost index, which is now index equals 1, right? And so from this point on, it's like, okay, this 0, okay, it is a 0, so we need to swap it, right? And so here, how many times do we swap? It's going to be ball index minus leftmost index, which is 9 minus 1, which is equal to 8. And I'll prove it to you here, right? So here, we're going to swap. So 1 swap, 2 swaps, 3 swaps, 4 swaps, 5 swaps, 6 swaps, 7 swaps, and 8 swaps, right? And now we're at this index, we just finished, right? And we augment this to index 10, right? So let's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this is the 10th index. I think so, right? 0, 1, or maybe it's this one. Okay, this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we're at this 10th index, right? And then from this point on, it's like, okay, I'm just gonna put a space there just to help me out. But now it's like, we know we wanna be at leftmost index, right? And so here it's like, okay, we see a 1, we don't need to do anything, so let's augment by 1, right? We see a 1, so let's augment by 1. We see a 1, this is a black ball, we augment by 1. We see a 1, we augment by 1. Did I make a mistake here? 12 to 13, then to 14. So this was the next 10. Okay, I was at index 10. After this, it'll be 11, 12, 13, 14, 15, right? Okay, so at index 15. And so now from this point on, it's like, okay, how many swaps do I need? So let's just keep going, right? It should be ball index minus leftmost index unless I made an error here, right? So let's just try this. So that's 1 swap, 2 swaps, 3 swaps, 4 swaps, 5 swaps, 6 swaps, 7 swaps, 8 swaps, 9 swaps. Notice we're only moving the 0 by 1 at a time, right? 10 swaps, 11 swaps, 12 swaps, 13 swaps, 14 swaps. So maybe this should have been a 14, right? I think I might have miscounted. But the point is it's ball index minus leftmost index, right? And then the point is that, like, you know, you increase this guy by 1, you increase this guy by 1, and so on. And you essentially keep doing it, right? You want the leftmost 0 to go to the first leftmost index. Then the second leftmost 0 to go to the second leftmost index, and so on and so on and so on. And then once you've essentially shoved all the zeros to the left, like we have done in this problem, we'll go through the rest and check that they're all black balls, right? So maybe we're here and we're like, oh, this is a black ball, this is a black ball. So we keep incrementing our ball indices, maybe up to 17. And then we're at the end. And so we have essentially finished the problem, right? And essentially the number of swaps we've added was what was it? It was like 8 minus 0 plus the 9 minus 1 plus the 14 minus 2, right? Which is equal to 8 plus 8 plus 12, which is equal to 28 total swaps, right? So in that example, it would have been 28. And so essentially, it's just like at the very end, since we shoved all those zeros to the right, necessarily what remains on the right is all the black balls, right? So we've essentially, as we wanted, put all the white balls to the left and all the black balls to the right. And so hopefully that explanation kind of makes sense, right? So the idea is that I take whatever is the leftmost 0, and I want that to be at index number 0, right? So it's just its current index minus index 0, right? That's how many swaps, because again, you can only swap adjacents, so it can only get there one at a time, so it'll take that many steps to get there, right? And then the second leftmost 0, I'm going to put it at the second leftmost index, right? I might as well put them there. I don't necessarily have to, but since I have to come up with a minimum number, that one definitely is going to be the minimum, even though there might be other ways to get to the minimum. I don't know. But I might as well, like, it's intuitive, right? Whatever 0 is leftmost in the string, it might as well go to the leftmost index, right? Because some 0 has to go to the leftmost index, so why not the one that's leftmost in the string originally, right? Even though it doesn't really matter, right? So if I put the leftmost index at the third leftmost index, then it's like, okay, I'll have to do 2 less with that 0. Well, actually it does matter, right? Because it's like, if I put, you know, this 0 at that index, right? And I don't move it, and then I have a 0 here. Then when I swap these two, then I'm gonna swap these 2 zeros, right? And then this, and then this. I just did one more unnecessary swap than I needed to. So actually, now that I think about it, we have to do it this way, right? We have to take the leftmost index, leftmost 0 and put it at the leftmost index, right? I just did that because that seemed intuitive to me, but actually now that I realize there's this little counterexample that we have to do it, right? Because the point is that, like, when we swap these zeros together, it effectively does nothing, right? Like if I swap these 2 zeros together, it's as if though I did nothing. But that takes one more swap, which means that this is definitely not the minimum, right? We just did a useless swap. So we actually have to take the leftmost 0 and put it to the leftmost index, which is probably intuitive anyways, right? And then whatever there's a second leftmost 0, put that to the second leftmost index. And it's just very convenient to calculate it, right? Because it's just whatever index of 0 it has, and the index that you want it to be, you just subtract those 2 indices, because again, you can only swap the 0 one at a time. So it's just gonna be the number of indices between those 2 indices in total, right? And so essentially you just do this for every 0 until they're all at the very very left, and then bada bing, bada boom. You're essentially done with the problem, and you just return num swap. So that's how I was able to do this problem. So hopefully the explanation makes sense. And yeah, so otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.